So we talked a little bit about field data collection of survey data, vector data. We're not going to get into details in this class because there's a lot of survey offerings from the university, but essentially survey data can either be data that you've gone out and collected with conventional survey methods using angle and distance measurements, either from really basic survey tools or more advanced electronic survey tools, or using GPS. So if you're looking for high accuracy surveys, we still use conventional survey methods to get the really precise measurements. GPS equipment is improving, and we've made huge strides in our satellite networks over the past 25 or 30 years, but that's still considered lower accuracy data. Some of the trade-offs are starting to change. Some of the conventional survey equipment is now about the same price as a high quality field GPS. So some of the price differences are changing, but there's still that element of what level of accuracy are you looking for? Are you trying to measure curbs and structures within inches or centimeters, or are you trying to lay out a street system within a larger area network? So those are the trade-offs that we look at when we start thinking about field collection. And it's important to understand those trade-offs when you get that data back into the field. If I get a set of spatial data from my survey department and I bring it into my field map, like I've done for this project we're going to kind of use throughout today. I know that each of these pieces that was measured by my survey department was measured with very high accuracy. Each one of these trees is absolutely referenced to a very precise spatial coordinate versus going out and collecting boundaries of an area with a GPS. When I do wetlands mapping, I take a handheld GPS and I go out and I walk the boundary of my project area, and I try to hold the GPS, over the ponds that I can't step in and get around and get a somewhat accurate boundary. But I know just by the nature of the tool that I'm using that it's only accurate within probably 3 meters at the very best. So I have to bring that back and use other spatial data to make sure that it's accurately represented.
Why were only some of those trees? I mean, it looked like it was a whole forest, but there was only a few trees picked. Are they like based on? Are they the tallest trees in the area, or the biggest diameter? Or
it's actually based on diameter, yeah. So typically, when you do tree surveys, you're looking at a trunk diameter. For wetlands mapping, if I'm assessing tree coverage, whether or not it's a shrub or a tree is based on the diameter of the trunk at essentially eye level. So, yeah.
That's pretty interesting. So it's all the big trees in the area are the ones that are shown as little trees right there.
Yeah, and all the little scrub spruce are not going to get collected. And I'm not sure exactly what the specification was for this survey, but yeah, they had some trade-off of which trees they collected. They also noted some trees that had eagle nests in them. So yeah, I can pull this data in and then I can combine it with other data from other sources. Obviously, this background image is a pretty high accuracy, really good quality LiDAR image that the borough collected, paid money for, versus some of the free data sets that I use that are lower accuracy. And you still have to look at, if I were going to go through and digitize a road from this feature, I probably would have a slightly different road boundary than the survey department collected. So some of that could be the oblique angle of the airplane that was looking, the direction from which they were looking. You can see there's some shading. You're not going to be able to see the edge of the road along this border as accurately because of the tree cover versus this side. So knowing that my road boundary here that I'm using was collected using conventional survey techniques, I can assume that there's a little bit of a shift in the image. If I had a data set that was collected using a GPS or was rectified from an image, I would know less about the accuracy of other images. So those are really important trade-offs to consider when you're understanding where your data came from into your GIS system.
Brenna, I beg your pardon. Can you define conventional survey techniques?
Somewhat vaguely, not being a surveyor, but survey techniques that use precise measurements from monuments, typically. So you have a monument with a very carefully referenced spatial location. So typically, if we're trying to translate that to a GIS location, it's either measured with a long period data collection. So I'll set up a GPS for a minimum of 3 hours over a coordinate system, probably longer, and then use a network of other GPS to correct that position. So then you know the position of all of your control monuments within a high level of accuracy, and then all of your measurements are taken off of that using conventional survey equipment. So they use high quality optics to measure angles between measurements. So if I have somebody standing with a GPS or a survey rod over a monument, I'll measure using this optical equipment the angle to my next measurement, and then also use that as a rangefinder.
Okay, so a long time ago, I was trained with a theodolite and steel tape.
Yeah, and that's one set of equipment that they still use. Typically, they use digital theodolite systems to expedite things now, but a lot of the techniques are really similar. And again, I'm not a surveyor, so I know a fair amount about collecting tide levels with a survey level, but very little about horizontal positioning with survey equipment. So. But often those are tied into geospatial systems, our coordinate systems, using long period data collection with a GPS to tie that information back to a coordinate. And so then we talked a little bit about using collector. You can use ArcGIS collector or a similar app with an external GPS. So I sent somebody out a couple of weeks ago with this setup, and they had a little external Bluetooth GPS. So it's more accurate than the internal GPS in your device, in your phone or whatever you're using. If it has an internal GPS, it's using an actual external GPS, but it's still not receiving high accuracy corrections from a GPS network. So again, the accuracy of that system is gonna be diminished. But you have the advantage of being able to take your GIS into the field then and collect points and make notes while you're standing there and looking at it. And there's huge advantages to that as well. So then you can bring that data back to your GIS system in your office and potentially use survey equipment to help correct those positions and make all of it a little bit more accurate. So there's iterations of all of these processes from field collection to office review to going out and collecting more information if you need to get more detail or information about change over time that you can then collate in your GIS system. So we've talked about that a little bit on and off, but just wanted to include that again as one of the means of getting data. The other aspect of field collection, which we don't really think of field data collection because we're not going out in the field and doing it, but remote sensing is field data collection, and remote sensing with satellites is also field data collection. So the satellite is out there in the field, it's an unmanned system, so we're not out there manipulating the data collection, but sometimes they are manipulated remotely, right? There is some level of control that can be exercised over certain satellite systems. You can order specialized imagery from different satellite systems for thousands of dollars, and they will take one little second of their orbit to collect a specific image that you're interested in and sell you that. So that is a form of field data collection, and there's a lot of different types of information that we can collect depending on the types of sensors that are built into these satellites. Some of them are passive systems, so they're just using information from the Earth. So like the first example here, a remote system sensing with passive information reflected from the sun's rays. Or the satellite may actually send out some sort of source to then bounce back and get information from that source. And there's actually, I linked an interesting article here that talks a little bit about passive and active sensors that are incorporated in some of NASA's satellites. So if you want to read a little bit more about that, I will have this lecture posted up after the class. So one of the really important things also to understand, just as we had trade-offs in accuracy in our field collection, we have significant trade-offs in our resolution and accuracy of our raster data collection, so our satellite data that we've gone out to collect. And sometimes that's spatial, right? Spatial resolution is a pretty obvious trade-off between certain different systems. You can instantly recognize if you have an aerial image that is accurate to 1 meter versus 10 meters. Over time, our satellite imagery has gotten almost scarily high resolution in some areas. But there's other types of resolution to satellite imagery depending on what type of information you are collecting. So if you're using one of the non-visual spectral bands to collect information, so if you're using infrared light, then you may have a different resolution in your data collection. So a lot of the satellite images that you see are printed in the blue, green, or red spectrums, or they're collected in a near infrared spectrum and translated into some sort of color that we can visualize so we can interpret the data. And then you have radiometric systems that are also similarly collected using electromagnetic energy from the sun's rays, but translate that into color that we can interpret. And that information is frequently used in things like vegetation classification, understanding heat maps of the Earth, or looking at things pertaining to the weather or ocean currents, ocean conditions. So when we're trying to understand things like sea ice change over time, we tend to use satellite imagery of that nature. So that's another good transition into the concept of temporal resolution. So all of these satellite systems are orbiting the Earth at different orbits, different periods. And depending on how their orbits are set up, you may have different availability of data collection over the same area of the Earth at different intervals. So if you're trying to understand sea ice change over a broad period of time, you can probably collect that at intervals that are spaced more widely apart. But if you're trying to understand short-term changes in how weather systems are developing, then you're going to want a satellite that's not orbiting and not leaving that area, probably one that's located in an orbit that stays in place over the Earth. So all of those are aspects of the resolution of your data. So resolution just means essentially how much detail you can pull out of the information that was collected, whether that's spatial detail, temporal detail, or detail in the variation, which is usually expressed in color. So I wanted to help you guys look at a couple of different types of data and understand how you go about assessing the accuracy, because it's not always obvious or easy. So the 3-depth elevation program is the program that US GIS is taking the lead on developing for our country, and that's what we're developing most of our elevation data sets from. And it's compiled from a pretty wide variety of data sources that have some variation in accuracy and resolution. So let's see if this is the link I was looking for. So these are examples of 2 of the USGS 3-depth information sources. And you'll notice if you read about Alaska in the 3-depth program, they talk about how different we are and how they're working on it, and eventually they'll get there. So there's a variety of different different resolution qualities available for the 3-depth program, and typically have to do with how much interest there is in an area, right? We're not going to spend a lot of time and money collecting high resolution data over an area that people don't care about as much as a city or a region that has a lot of people and development. So in the continental US, that ranges from 1 arcsecond to 1/3 arcsecond. So those are based on geographic coordinates, right? We talked about gridding the Earth in different ways. And when you're using a lat-long grid system, the spacing between your lines varies depending on your distance from the equator. So we talk about things in terms of arcseconds, which is a fraction of a degree, in order to talk about them in a way that's comparable. But that can vary, especially when you're talking about Alaska versus the lower 48. The amount of distance in 1 arcsecond can vary significantly over that area. So that's why they use the language here, approximately 30 meters in an arcsecond, or approximately 10 meters in 1/3 arcsecond. So for Alaska right now, we have full coverage in 5-meter resolution, and I think a lot of it in 1 arcsecond, but only parts of it available in 1/3 arcsecond. So that just gives you a little bit of background on what they're talking about when we look at the USGS 3-depth systems. So this is an image near King Salmon that was collected, and this one is a 2 arcsecond. So if you look at the information for that, a 2 arcsecond grid is approximately a 60-meter grid. So you're not going to use this for mapping if you're trying to lay out your plan for construction of a project site, right? If I'm reorganizing buildings in an area, I'm not going to look at 60-meter grids for my elevation, at least not for long. I'm going to go out and I'm going to collect some more accurate elevation information, or some more higher resolution elevation information. But for that same area, there's also a 1/3 arcsecond image available. And that 1/3 arcsecond image has a resolution of approximately 10 meters. So that's getting a little bit better. I can start to understand elevation change over a much smaller area. Still probably not high enough resolution for a really good site layout, but enough to start looking at maybe my gradient over the area in general, and start looking at maybe hydrology. But of course, everybody always wants higher resolution, more data, but they don't want to store it on their computers because it takes a lot of room. So that tells us about the resolution of this data, but it doesn't answer the question of how accurate this data is, right? I can have a very high resolution image be totally inaccurate in its spatial location. So you have to do a little bit more digging to get the answer for that for the 3DEP program. And even then, you have to understand what that answer is telling you. So for 3DEP, if you go looking for information about accuracy, they tell you that the 95% confidence level, it has a vertical accuracy of 3.04 meters. So that means any given point of elevation, if you compare it to a known project control, is going to be accurate within 10 feet. So if you're laying out buildings, again, knowing the elevation of your building within plus or minus 10 feet, it's probably not good enough. But knowing the change in elevation in a larger area within 10 feet might be plenty good enough if you're talking about something like hydrology or estimating the effort to get things from one elevation to another location. So does anybody have questions about what this accuracy means and what these different resolution descriptions mean?
So for this 3DEP program accuracy, it's mainly just for large scale type operations. You wouldn't, I mean, for everything you just said, you wouldn't build a building based off of that, right?
Right. So for this project that I'm showing you, there's definitely 3DEP information available, but the LiDAR data, let me see if I still have my contours. I don't know what I did with my contours, but the LiDAR data that I'm using for contours is not the data from the 3DEP. It's definitely a data set that was collected for the Kenai Peninsula Borough. So this was flown with airplanes at a much lower elevation. So you're getting much higher resolution. And they're also laying out a planned control program for this project. So they know the accuracy that goes along with this data based on their comparison to the control that was placed for this project. So for the 3DEP system, there's no stated horizontal accuracy for this program because it varies substantially. In fact, there's a way you can report errors in the 3DEP program. Lost it now. If you locate them in your project area, if it's way off, you can report it to 3DEP. But they do know overall their confidence level for vertical accuracy. So another important trade-off when you're looking at the reliability of data sources, right? I can rely on the changes that I see in this information being spatially accurate to some degree when compared to the 3DEP program. But I'm still not going to trust this information over my surveyed information, which they also, I'm not showing the elevation data that they collected, but if I had a need to do assessment of elevation, if I was trying to understand stream flow through these areas, I would emphasize their data over even this LiDAR data set. And that's one of the ways that we use the survey data that our survey crew collects is to make models of surfaces and look at hydrology of these systems. So when we have these two different questions, right? What's the resolution of our data and what's the accuracy of our data? So I just wanted to show you guys two aerial image sources. This is that same project area in King Salmon that I was looking at the 3D surfaces for. And one of these is an aerial image from the best data layer from the state of Alaska, which is an aerial image flown with an airplane, most likely. And one of them is the Esri world imagery, which is collected from a lot of different sources. The question of which of these is more accurate is entirely unknown based on the information that I've provided you. So if I was going to go out and try to digitize buildings from these images, I wouldn't know which building was the true building unless I had other external information. Probably would start looking for control information in the area or road layouts from other sources to try to assess which of these might be more accurate. But then you have to be very careful with that information as well. You have to know where that vector data information came from. Did somebody take one of these images and digitize the road systems and call that their road infrastructure database? Because that's a very common way to approach that in communities that can't afford higher accuracy mapping. Or is that a high accuracy set of control information that was collected by a surveyor? So again, just an example of, you can't really see both images here, but you can kind of see from the after image that both of these images are high quality, high resolution images, and they're ever so slightly different and different in different amounts over the area that we're viewing. So there's some distortion in there as well. So how would you estimate the spatial accuracy of this USGS digitized slide? This was collected with a USGS aerial camera overflown. I can't remember, I think it was like a early 1970s or late 60s flight. And it's available from USGS Earth Explorer. Some of you guys used images like this. So what do you remember from the Earth Explorer exercise that I did for you? How accurate was the positioning of some of these images? Anybody? I know some of you use some of these. Well, if you use this one for an example, it's not even close, right? Sideways. So another thing to keep in mind is not every aerial image is positioned even correctly. Sometimes we collect raster images and we think of them as aerial images, but they haven't actually been spatially located by a survey professional or a spatial GIS professional. So take your spatial positioning with a grain of salt, because that is not the direction in which that river flows. So how do we figure out this information? It's really important to look over the metadata of the information that you're provided. So a lot of these data sets arrive in packages and they come with reports. It's a good idea to at least glance through that information when you get it, in order to understand, because it's especially when you have high resolution data sets like some of these, it's really natural for us as humans to start making assumptions like, okay, I can see very clearly where things are laid out. And then my next logical assumption is that they're laid out correctly. And that's a really easy mental trap to find in. I think I told you guys earlier in this season, I made some pretty big mistakes on a wetland data collection because I assumed that the boundaries that I had downloaded were correctly positioned. And I used those to select an image that I thought was correct and use that to correct the positioning of the data that I provided my client. Come to find out later that the base assumption there that the boundary data that I was using was accurately positioned was false. And I ended up having to revise my entire report and all of the impact calculations that I had based upon that. So pretty big mistake, and definitely something that I should have known better. So I have to live with that mistake and apologize profusely to that unfortunately new client. So, and hope that they understand that I will not make that mistake again. So ways to do that are to compare them with a lot of other data sources, and then make sure that you have a good understanding of where that data originated and how it was collected. It may not seem important at the beginning of your project, but by the time it becomes important, you may have made several assumptions that built upon that initial assumption. So it's a good idea to know, understand your sources as they come in, and then use other available sources to quality check your data. And you might wonder, like, how much effort should you put into this? How much does it matter how accurate that is? And that's entirely dependent on how you plan to use that data. But keep in mind that your data usage might change over time, right? A client might go out and collect, they might pay somebody money to collect all of this lame information and digitize it and put it into a GIS data set, and not understand that the positioning was entirely at the whim of the GIS analyst that geolocated these using the built-in georeferencing tool in ArcGIS and didn't necessarily have high accuracy control to base that upon. And they may hand that to you as a data source, and you might make assumptions down the road about how accurate that is. So it's important, like, to check in along the way and understand how your usage might have changed, right? They might have done that to do an initial community layout and do some community planning on a large scale, and then assume that they can use it further down the road when they're starting to get into site details. So that kind of touches on a few things that we've talked about before, but I hope emphasizes some points as you go into creating your maps. Again, I'm not expecting you to go out and collect high accuracy data where it doesn't exist, but I do expect that you understand the accuracy of the data that you're working with and how it might play into what you're building. So geocoding is a pretty common problem when you're working with geospatial databases that pertain to a community. So one of the things that you might do mapping for is to understand the part of your community that needs to receive a public notice or positioning information along a road network, so the people using your map know how to arrive at the different locations. And so there's this tool that's been developed over the lifetime of GIS, essentially, to take spatial coordinates. So you'll have a lat long of a position, or you'll have something that you can, a XY coordinate from another system that you can convert to a lat long or import into your GIS, and then use the tools built into your GIS to determine an address. And as you might imagine, for something that's essentially relying quite a bit on Google Maps, address database, and the United States Post Office, that's not necessarily a one-to-one, really straightforward relationship, right? We don't have perfect mapping of the entire United States. We have far better than we did when those tools were first developed 20 or more years ago. I remember driving around with the first really cool GPS with a built-in mapping program and thinking, wow, that map almost makes it look like we're on the Seward Highway. Things have improved significantly since then, but taking that information and turning it into a mailing address is another step of accuracy, especially when you're trying to mail out things that are critical to actually reach the right people. So there's some cool tools built into ArcGIS Pro for that. And I believe there are some plugins, some external tools available for QGIS to do the same. And they rely on some open source systems that collect this information and then provide you ways to quality control it. So one of the, I didn't build in, so there's a geocode function in ArcGIS where you import essentially a table that you've laid out containing all of your address information. So you'll have your street address in one column, your city in another column, your state, your zip code, and you'll import that into ArcGIS. So that's your address string, and then it will output coordinates. And if you do it in ArcGIS Pro, it will also plot those coordinates for you. Or there's online free sites out there that'll do the same thing for you. You can input lat long or XY coordinates, and it will spit out addresses for you. But there's some advantages in doing it in a little bit more sophisticated system. So in ArcGIS, once you geocode your table of addresses, you can use another tool that they have, which is rematch addresses. And that lets you go through and identify ones that might have slightly confusing addresses built in, like this example that they show didn't have a zip code assigned. And there could be other similar addresses that match better. So this one suggests that the 30308 zip code is the most likely match for the Northeast. There's a Northwest version of this address that doesn't match quite as well, or there's one building off essentially that matches even more poorly. So these databases actually include parcel information that says, okay, there is a 150 6th Street Northeast, but there's also a 150 6th Street Northwest. They wouldn't suggest this address if it didn't exist. So if there wasn't a parcel out there, it wouldn't be included in your list of suggestions. So that's one of the tools that's powerful for this. It's not just generating possible address combinations, it's generating existing addresses that might be true. So again, this is only as useful as the quality of the data, right? If there's say there's a new subdivision developed and there are addresses within that subdivision that are in the process of being assigned, this would probably fail for those locations. But it's a good tool for addresses that have already been vetted. So it's probably one of the reasons if you use online systems quite a bit and you enter your address, say you try to mail something online using the post office website, and they will suggest an alternate address for you. That may be due to formatting, and it may also be due to the fact that your address, the way you've entered it, doesn't exist in these databases of existing parcel addresses. So another tool that is as good as the data in and the quality control of the person using it. So this is one of those tools built into ArcGIS Pro that requires that you have an online subscription. So if you have any mass mailing to do, I suggest you do it now while you have a license. But again, there's other online systems that do that for free. Oh, I put the wrong image on this one. So there's also the opposite direction of this, right? If you have a set of point features, which might be a little bit more likely way for us to want to geocode. We've created a map and we've laid out our road network and we've identified points of interest, and we want to assign addresses to those points of interest. There's the reverse geocode function, which looks a lot like the rematch one, but I've unfortunately added the wrong image. Apologies for that. But that one also requires an ArcGIS online subscription. So that's built into the current licensing that you guys have as students.